Hello, my name is Eduardo Lopez,
And I'm Seth Falcon.
and this is our TEG and Me science project. So, the purpose of this experiment is to study the effects of the Seebeck effect, in which where you heat up the one end of a metal rod and you cool off the other end of the rod, which produces a voltage or a millivolts through the rod, which can be measured with a multimeter. And this is the Seebeck effect, and this can be used to create voltage, create electricity. And this is we use this within our experiments.
Okay, so first of all, what even is a TEG? Well, a TEG, or better known as a thermoelectric generator, is a generator that uses a cold end of a metal rod with a cold end and a hot end. In this case, we're using a copper rod. So the hot end, which is the N type, as you can see, which is the blue block, um, a those yellow dots are electrons, and they're trying to go to the positive type, the green block, which is the cold end. So as the electrons are moving to the cold end, just think of it as like diffusion, as homeostasis. They're just trying to fill in those holes, and whenever they fill in those holes, they produce voltage, and that's basically the Seebeck effect.
So our question and our hypothesis. So our question is, through the Seebeck effect, will the voltage produced from the change in temperature on each end produce more voltage through the copper rod? So our hypothesis is that if we increase the temperature of the hot side and decrease the temperature of the cold side applied to each end of the copper rod in unison, then the voltage produced from the temperature difference will increase within the copper rod. So through the Seebeck effect, we we think that there will be an increase in the voltage if the temperature is increased on one side and decreased on the other side of the copper rod at the same time.
Okay, so here we have our materials. So we use a copper rod, and then for a heat source, we use a burner. For our cold source, we use a cup with water and ice. And to measure our millivolts, we use a multimeter. And just to for easier access for the wires, we use a 3-liter Coke bottle to stand the copper rod upright. And to uh, uh to measure the to measure our millivolts easier, we had to drill holes on each end of the on each end of the copper, which is the hot side and the cold side, just for just a safer process. And and lastly, we use the thermogun to measure the temperature.
So our variables, so we have our dependent, our independent, and our control. So our dependent variable was our voltage, and this makes sense as through the Seebeck effect, the voltage is dependent on the temperature, which also means that our independent variable is our temperature. As when our temperature increases and decreases on each side of the rod in unison, our voltage will change. This also means that the control in our experiment is the copper lead. And this is because throughout all the trials and the controls in our experiment, the copper rod was always the same, no matter what we did, no matter if we increased the temperature, we decreased the temperature, or we measured the voltage, it was always the same copper rod throughout all the experiments.
Okay, so first, we set up our stand, and we put our copper rod through our dealer Coke bottle. Tip we tipped it down, and we tied one end for our second step. We tied one end and to our burner, as that will be our hot side, and then we submerged another end, our cold side, and water and ice. It's important to note that we put salt in our ice just to insulate our our cup with water, our ice, because a cup with water and ice melts slower than a cup than just a cup with water and ice. And then third, we measured the no, we tied the wires. It's hard to see, but you can see the red wire, which is uh which is the cold side, and then our black wire, which is for our hot side, which is the negative side. And then for our first step, we basically measured the millivolts and recorded temperatures. And for a fifth for a fifth step, we analyzed the results and recorded it in the table.
So, in our experiment results, these were the results that we had produced from our experiment, as said from the procedure before. So, as you can see, we have the hot end of the temperature and we have the cold end of the temperature. So, you see the high end has an increasing temperature as we go down each trial, and the cold end has a decreasing temperature as we go down each trial. And you can also see the voltage increase from 1.0 to 2.5 to 3.0 millivolts, which is our highest. You can also see that we had this extra data showing the negative probe's temperature, which was the hot side, and the positive probe's temperature, which was the cold side. We had this extra data just to show that there was a difference in temperature on each end where we actually measured with the voltage. But in reality, what matters most in the feedback effect is how hot the hottest the rod gets and the coldest it gets on each side, which would be the cold end temperature and the hot end temperature. So as you can see, our test, which is our control, we left each end by itself at room temperature, which was 75 degrees. And we left it for all, which meant that our final millivolts measured was zero point 0.0 millivolts, as the feedback effect had not been initiated yet, so no current was being produced. But as you can see, as we go from trial 1 to 2 and 3, we see as the temperature increases on the hot side from the fire, sorry, my bad, as the temperature increases from the fire on the hot side, and the cold decreases on the cold side, voltage is increased steadily, as we can see from 1.0 millivolts to 2.5 millivolts, and finally our highest volts reached was 3.0 millivolts. And this is as shown from the decrease in temperature going down and the increase in temperature going down each trial.
As you can see here, these are pictures of the recorded millivolts for each trial. So the first trial, which was our lowest temperature for the cold side and the hot side, was 1 millivolt. And then for our second trial, we increased the hot side temperature and decreased the cold side temperature, and we got a higher voltage as a result. And then for the third trial, which was our hottest temperature and our coldest temperature for both cold side and hot side, was the largest amount of millivolts that was produced.
So in the analysis of our data, we had seen that throughout each trial there was a definitely an increase in the voltage received, voltage reached. As we see in trial 1, the hot temperature and the cold temperature was at its lowest, saying that the hot wasn't as hot and the cold temperature hadn't gotten cold yet, meaning that feedback effect was at its lowest efficiency, but it did produce a voltage which was the 1.0 millivolts. As we can see, though, once we increased the hot temperature and decreased the cold temperature on each side, there was an increase in the voltage. As in trial 2, where 2 degrees was added to the hot side and about 5 degrees was added to the or decreased to the cold side, there was a significant increase in millivolts as we reached 2.5 millivolts. And then finally, in trial 3, it is shown that at our highest recorded heat and then our lowest recorded cold side, the temperature for the cold side, when we met those criteria, we had reached our final highest voltage, which was 3.0 millivolts, which was the highest voltage we had reached in the entire experiment. And this was at our highest temperature for the hot side and our coldest temperature for the cold side.
So in conclusion, as a brief reminder, our hypothesis was that the differentiation in temperature would increase the amount of voltage that was produced. So in this case, well, let's recap. So we started from room temperature, but as we exponentially decreased the cold side temperature and exponentially increased the temperature, and as we seen through trial 1, 2, and 3, the millivolts was actually increasing. So it was from 1 to 2.5 to 3. So in fact, it did the temperature differentiation did increase the voltage, and therefore our hypothesis is correct. So some negative factors that could have impacted our experiment was the consistency. So we basically have like a high accuracy and low precision result. So we we didn't we our temperatures were like from a range, as 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 mentioned before. It's growing. The temperatures were growing exponentially, so we couldn't really record like the exact temperature for the exact millivolts that was produced. But basically, we got to our point. We know that temperature was increasing, temperature was decreasing to the results, and therefore, we can prove our hypothesis correctly.
So, in our final remarks, as my partner said, there was some inconsistency in our experiment. we did have a high accuracy but low precision, as in we had a high accuracy that our voltage was exponentially increasing as we saw through each trial, but we had low precision as it was really hard to measure each temperature equivalent to the actual millivolts reached. But it all in all, we did reach our hypothesis, which that it was true that if we increase the temperature on the hot side and decrease the temperature on the cold side, we would increase the voltage, as we saw, which our highest voltage was 3.0 millivolts. So our science experiment shows that the potential this technology has for possible small amount of electricity, and it can also be added that these devices can be paired up with other ones exponentially, so you could get more voltage if you add more and more on each other. Our demonstration was a very small example of just one lead. We could do the same thing with many leads, and we would increase the voltage as we increase the heat and the cold. And through this, we can show that we could power small devices such as light bulbs, phones. We could charge phones. We could even power small smartwatches that go on you that use your body heat and the difference on the other side of the heat of the cold to charge the smartwatch. Now it might be a low voltage, but it is something. It is something. It's not just nothing, as the feedback effect shows. And as we've seen, our experiment, we think that this experiment shows that we should research more into this subject that of the TEG, or the thermoelectric generator. It has lots of possibilities and lots of things could be achieved with the such technology. We should just research more into it and see the positives and negatives that this technology could possibly bring. But we believe though that it is most interest to keep researching and see the full extent that which the TEG, or the thermoelectric generator, can take us. So these is our final works cited. This is the end of our presentation. Thank you very much.
Thank you for watching.